Tous, merci de venir pour ce séminaire qui a un horaire un peu pas usuel. Donc on a le plaisir aujourd'hui de recevoir Benny Davidovitch. So Benny Davidovitch is a professor of physics at Amherst near Boston. So he's a specialist of the mechanics of thin solid films, wrinkling, instability, and this type of behavior. And so today Benny will tell us about the dynamics of another type of thin films, which is a liquid viscous thin film. So thank you so much for coming here for presenting today.
Thanks very much, Arno. Thanks for the invitation, and to Sebastian, who is not here, unfortunately, but great to be here. Yes, so I'm going to tell you about a work that I've been very excited by, about a problem that I've been very excited by in the last 3 years or so, since I tell you about the history of this work, of this problem a little bit. But I'll give you just, one thing I forgot to bring with me, I was hoping I had, but I forgot, and is a soap, like, you know, this soap bubble blower, right? I mean, so try to imagine that this, just now I'll show you a few bubbles, and you know how this beautiful this bubble look like. And we are attracted by their color, by their shape. If you can, you know, you can put them on various type of frames and you get very complicated structures. But eventually these bubbles are die, right? I mean, they don't stay long forever. Typically what would happen is that a hole will pop somewhere, and once the hole is popped, two things happen. The hole opens up, and the other thing that happens is that the air, the pressure between the interior and the exterior of the bubble equalizes, and then there is nothing to support the spherical shape of the bubble. And the question is how this dynamics happens. And if you try to do it with soap bubble, it happens too fast for you to see anything. The other things about this dynamics with soap bubbles is that soap bubble is a really complex fluid. In order to see this, to manage to make these bubbles, you have to put quite a bit of surfactants inside the container where you put the simple liquid. And if you want to do it in a very simple way, so this was the first idea to study this kind of behavior was due to Debregeas, Dejean, and Bouchard. And I was just told that Professor Debregeas is here, so I'm very happy to give this talk. So they started to look at the problem with thin films, thin, very viscous films. So if you want to blow a bubble, but you don't want to use a surfactant, you can do it with very viscous liquid. Okay? Glycerol may work, I'm not sure, but what can work is silicone oil. Silicone oil is a liquid whose viscosity is like 1 million times more than water. And it's a simple liquid, no surfactants, just a basic pure liquid, very viscous, and you can make nice bubbles with it. And what the problems that I'm going to tell you about is how such bubble made of pure liquid, just very viscous, how it collapses when the air is on the interior and the exterior is becoming equalized. Okay, so the original experiment was done by Debregeas. I believe it was a PhD work at the time. Okay, and then it was followed up by the group of Mahadevan in MIT with Rava DaSilviera, who I believe is also somewhere around here, or I don't know exactly, but this was Rava DaSilviera. Later, like a few years ago, it was finally followed up again by Alexander Oratis, who was a PhD student in the lab of J.C. Baird. Each of these were a science paper, if it matters for anything. Yes, so what I'm going to show you now is a movie of how these things happen. So what you see here is a viscous, this bubble of silicone oil. It's not freestanding, okay? It's not like the bubbles that you make and blow in the air. It's floating on a bath of liquid. It's like what you would have in your bathtub if you see bubbles. So it's only a hemisphere, only half a sphere. And there is lots of crap here, which is mainly optical artifacts. So don't pay attention to all the lines. What you see here is just the bubble. So it's a film, liquid film, very thin liquid film. Inside there is air. The pressure of the air is somewhat larger than the pressure in the ambient air. And this is the silicon oil bus. So the way it was made is by injecting some air bubble inside the bus and letting it floating upward. And you may not see it, it's maybe not so obvious, but there is a meniscus here. Okay, the meniscus is where the film, the liquid film, connects to the liquid bus. So there is a meniscus there. Everything is silicon oil. Okay, and now I'm going to show you the movie at how this bubble collapses when the air depressurizes, and we are going to see one thing. So you see the airdrop pressure, and you see this beautiful instability. Something happens, right? I mean, we see these lines that the film becomes unstable. Okay, beautiful picture. The whole period here is, the whole film is like 1 second, or a little less than 1 second, which is extremely, extremely fast for silicon oil. Okay, it's so highly viscous, so it's extremely, extremely fast. And everybody saw the instability? Okay, you see something, it does not. Okay, and now I'm going to run the movie again, and I'm going to ask you now to pay attention to two other things in this movie that should attract your eyes, but not the instability. Okay, the instability we already noticed, now two other things. So try to, especially the experimentalists of you, or not only, but everybody, should try to notice two interesting things. Or at least two aspects that are worth noticing. Okay, yes? Eventually it flattens, yeah, but it has to flatten because the air drops and the film has to merge with the bus eventually. Maybe other things? Anybody see a hole, a rupture? There was no hole, right? I mean, so that's one thing. You did not see a hole. Okay, I'm going to, that's one thing. The other things that you may have noticed is that the meniscus doesn't move. Okay, so basically the bubble collapses not like in a way you would expect from a freestanding bubble to collapse, which just shrinks. Somehow its edges in the where it connects to the bubble is like sort of clamped. Okay, not moving in the time of the process. Okay, so these are two important things that we'll pay attention to. And now I'm going to describe this in a little more detail, what really was the contribution of Alex. So the basic phenomenon, the instability, was already observed by Debregeas, Dejean, and Brochard quarter of century ago, which is like this, right? I mean, you have the bubble, the pressure is slightly larger than the ambient pressure. This is the Laplace pressure that holds it in a spherical shape. You come with a stick, you make a tiny hole. Once you make the hole, the air pressure equalizes very quickly between the interior and the exterior. The hole may also expand a little bit. Okay, and then that's what you see from the top. You see this beautiful, very ordered pattern of wrinkles. Okay. And what the major contribution of J.C. Baird and his group on this, which was really, I think, quite a remarkable one, was two things. First of all, they showed that gravity has no effect here. Okay, you may say that gravity should not have effect, but it was conjectured to have some effect. So what they did was to flip the whole setup upside down. And you can do it because it's silicon oil. It takes a long time for it to change shape. And you can see that basically, well, it may not be obvious from this picture, but you see this, you still see the same instability in these conditions. And even more remarkable, and this goes to what I mentioned in the beginning, JC realized that, you don't need a rupture to make this instability. So what they did is a very simple trick. They just came with a nozzle or with a hose through the bus, through the silicon bus, and just depressurize the air without touching the film. Okay, and essentially they saw the same thing. So that the film that I showed you indeed did not have hole because it was generated by this method. Okay, so you can get a rapid change of the pressure without making a hole. And okay, so now we know something about this process. And normally the questions that people asked in these previous papers, including the paper of J.C. Baird, was, well, you see a pattern. If you come from a tradition of pattern formation school, there are obvious things to ask. You see a length scale. What controls this length scale, this wavelength? how it depends on the viscosity of the liquid, on the radius of the drop, just name it, right? I mean, what determines this apparently emergent scale? This is one question. I'm not going to tell you much. I'm not going to tell you much about this question, although it sounds the most interesting. I'm going to tell you much more about this question, which I called question 0, which is why do we see an instability at all? Okay, this process is characterized by axial symmetry. Okay, axisymmetric shape, right? You have the bubble; it's a hemisphere. Even if you say that the edge is clamped, everything is axisymmetric. Why there should be at all an instability here? Why should we see something which is not just axisymmetric shape, the boring, smooth shape that collapses down? Okay. Of course, if it was the case, then none of this science paper would come into the world. But so I would not be here to tell you anything. But still, we need to understand why there is an instability at all. And it looks like this question was maybe sounds too boring or not worth of asking, or the answer seemed to be pretty obvious. And when I tried, well, I did not ask, for instance, Professor Debregeas what was they had in mind, or why there should be an instability, or other people. But I think that the rationale was, well, it's pretty obvious. There must be an instability here. Why? Because it's related to what I call the grape to raisin hypothesis. So what is the grape to raisin hypothesis? You can all do it in your tabletop, right? I mean, you take a grape. The grape is just a skin, right? Very stiff skin filled with more or less liquidy interior. Once it dries out the interior, the skin has to retain its area. Okay, so you have the same area now occupying much smaller volume, and somehow this excess area has to go somewhere, so it wrinkles. Okay, and why it's related to the problems that I just showed you, because, well, think of this, right? I mean, you start with a hemisphere. This is my original shape of the bubble. Now it has to go down because the pressure drops, so it has to flatten, and the area, of course, changes from 2 pi r squared to pi r squared, right? I mean, there is a reduction in the surface area. So this seems to explain why there should be an instability, or let me put it in more logical change. So there is a confinement of the surface area into a smaller, it has to be occupy a smaller volume. This generates compression, in-plane compression, and this compression, just like in elastic materials, it generates buckling or wrinkling, and the only question that we have to address is what is the characteristic wavelength in this instability. Okay? I want to tell you that this rationale is wrong. And why it is wrong? It's wrong because we can, to show you why it is wrong, I'll look at this problem that I'm going to discuss later on in the talk in much more detail. But for now, just try to believe me to what I'm telling you here. So I'm trying to look at the spherically symmetric version of the problem. Okay? So what I asked you to imagine in the beginning, so just imagine that you have a freestanding bubble, and now assume that it's very viscous, so you can totally forget liquid inertia. And now, so the equilibrium has some Laplace pressure inside that keeps this bubble in spherical shape. And just try to imagine that at time t equals 0, you drop this Laplace pressure to 0. So the pressure is now the same on the interior and the exterior. It doesn't matter how I do it, okay? Fortunately, I'm not an experimentalist, so I don't have to do it myself. I can just think about it as a good Gedanken experiment. Think about it, if you wish, as a thought experiment. Okay, so what would happen? So the bubble has to collapse. And what I'm showing you now is a schematic of an exact solution of the problem. Spherically symmetric solution of the problem. Here you have spherical symmetry. What happens is, I can show it again, we start with a thin bubble or with some thickness, and once you drop the pressure, it starts to collapse because the volume of the liquid, this is the blue thing, it has to be conserved, the film has to thicken, and that's it. Okay, this process is totally stable, linearly stable at least. It does not undergo any noticeable instability. And what it shows you is that this rationale is wrong. Okay, so here we have a reduction of the surface area, but this mere reduction of surface area does not generate any compression in the film. And why? Because the film can thicken. And this is different from solid bodies, where you have solid surface, you don't change its thickness when it undergoes changes, but the film can do it as easily as it can change the shape. Okay, so this is another degree of freedom that allows you to escape any compression. Okay? So that's basically the reason why the question of why there is an instability at all, why there is a compression, worth asking, worth studying. And all my talk is going to be basically on this, and I'm going to tell you that this is actually, we believe that the answer to this question is a peephole into a branch of hydrodynamics that I would advocate requires much more studying than what we have now. It indicates on some gap in our understanding of hydrodynamics that this problem calls us to start feeling. Okay, and so in my understanding, this experiment is a beautiful peephole into a interplay between viscous hydrodynamics and what I would tell you is interfacial thermodynamics. And at least theoretically, I'm going to put here an equation, and I know that I'm going maybe intimidating the audience. I'll try not to do it. I'll try to tell you why everything is in this equation. And what you see here is a second Laplacian. Okay, so you have a Laplacian of a Laplacian. It's a bi-Laplacian of some function. I'm going to call it a potential. Okay, psi. And it equals to something on the right-hand side. Okay, and this is something that I would like to call charge, similar to what we have in electrostatics. Okay, so you have Laplace operator operate twice on some function, and this is this what I have in the right-hand side is the rate of change of the surface curvature. And I would like to tell you that the process, this collapse of a viscous bubble, is one example, beautiful example of a solution of this problem. And why? And now what is this? So I try not to intimidate you so far. So those of you who are familiar with Stokes flow, Stokes equation, or a Stokes flow in 2 dimensions. So this is a realization of Stokes flow. In this case, you can think of psi as what you would call stream function, but not in a planar geometry, but in a curved geometry. Okay? If you are familiar from the hydrodynamics context. If you are coming from elasticity, for instance, the PMMH folks may, or probably other people, they may recognize it as similar to the Foppel-Van Karman equation of elastic sheets. The difference here in this case will be that what you have on the right-hand side, what generates stress in this problem is not curvature, is not surface curvature, but the rate of change of the surface curvature. Okay? And for each, whether you are in this community or that community or none of these communities, I would like to advocate that you all know, I assume, something about electrostatics, if you took first year of some physics classes. So this should remind you of Poisson equation. Right? I mean, so I'd like to build a lot on this analogy and try to tell you why, if you know some basic lessons from electrostatics, you can understand quite a bit of what's going on in this problem of bubble collapse that you see here. Okay? So that's going to be the sequence of my talk. I'll try to tell you why first. I will try to tell you more about this equation, where this equation comes from, and why it describes this dynamics that we see here. I'd like to describe that there is an axisymmetric solution to this equation, which gives rise, can be interpreted. Understanding this axisymmetric solution will tell you what is this axisymmetric evolution, which eventually becomes unstable. And it will tell you also why indeed it's unstable, because there is some compression here that eventually resolves into wrinkles, surface instability. So this will be basically the outline of my talk. Any questions so far? There is surface tension, yeah. Yeah, it's underlying here. So when I say stress potential, so it's a potential of some stress, and this stress is viscocapillary. It has a capillary component and a viscous component. Okay, and this will come through some stress-strain rate relation that I'm going to show later. Okay, and the elastic analog is just a strain. Okay, yeah, but we are going to discuss it later. Any other questions? Okay. Okay, so this will be the outline. I will just tell you about the introduction, about the puzzling instability. Now we are going to do a little bit of hydrodynamics. I feel humbled to give some hydrodynamics in this audience, but I'll try to do my best to tell you where this equation comes from. And then we will discuss the thermodynamics aspect of the problem and why there is an instability. And hopefully we'll all be happy at the end. Okay, so hydrodynamics. So here is a crash, 2 slides on hydrodynamics. So what is hydrodynamics? In my understanding of hydrodynamics, Landau Lifshitz, many other classical textbooks, it's a macroscopic flow which is characterized by local thermodynamics. So you imagine that each fluid element, each tiny element is in locally thermodynamic equilibrium. There is an equation of state that it satisfies there, but it's out of equilibrium because there is flow and not everything is the same, and there are some conservation laws. So what are these conservation laws? So you know from Newton that mass, energy, and momentum are being conserved, and the first attempt to generalize it to a continuum, to a fluid, was done by Euler in his what we call ideal or inviscid flow. In this case, energy, momentum, and mass are being conserved. I'm not going to write all these equations in detail, but I assume that you know what they are, and if you don't remember what they are, it doesn't matter. You should remember that these are the conservation laws that are being reflected in this equation. Okay? Some 60 or 70 years later came along these two gentlemen independently, Navia and Stokes, and killed the energy conservation, or more accurately, the kinetic energy conservation. And what they actually, they did not want to kill energy, as far as I know. All that they wanted to do is to allow momentum to diffuse. Okay, so momentum is still conserved, as Euler imagined. It's just that it does not have to radiate through waves, but it can also diffuse. Conserved quantity can still diffuse, and probably they understood, or not fully understood at the time, that by allowing momentum to diffuse, you imply that energy, or the kinetic energy in the liquid, is no longer conserved, it's being dissipated. Okay, and some around the same time, Posé and probably also Stokes applied these ideas into these equations into the most important physical application at the time, and maybe still now, which is pipe flow. Okay, and when you do pipe flow, you need to have a pressure gradients on two sides of the pipe, and the momentum or tangential momentum that you are providing by the pressure difference, it's all dissipated by the boundaries, by the walls, right? So basically in Posé flow, you no longer have momentum conservation. Okay, if you try to average out, of course, it's being conserved in the bulk of the pipe, but if you integrate over the cross section, it's all gone to the dissipation with the walls. Okay, and indeed, this is the form of the Posé equation. You see that this is the rate of change of the momentum of the liquid momentum. It's being dissipated, right? I mean, there is a term here which goes like the velocity, the viscosity times the velocity, it's dissipation of the momentum. Okay, it took another to the end of we're running forward to the end of the 19th century by Rayleigh, who studied mostly the plateau instability of how jet breaks, and Troughton, who formulated it later in a more rigorous way, mathematical way, that realized that there are situations in which you can still have flow in a narrow environment, but without dissipation of the momentum, and this is if the surfaces are both free. You don't have any walls to dissipate the momentum. In this case, you don't have pressure macroscopic, you cannot maintain macroscopic pressure gradient, but you can still have a non-trivial flow. And in this case, the momentum, you see this is the rate of change of the momentum, it's being conserved because it's proportional to gradient of something. In this case, it's the divergence of a tensor. Okay, so it's still being conserved. And what Rayleigh and Taylor and Troughton had at the time is that, okay, how do you generate such flow? So you need to have some thickness of the film, and if you have variation of the thickness, now you don't have a pipe, right? I mean, you have a free surface film, and if its thickness varies, this can generate local pressure gradient, and this is what pushes out the flow. Okay, so this was the idea at the time, and then again running forward to the mid-20th century, Mr. Taylor realized there is one of his many contributions was to realize that there are situations you can generate also free surface flow, again without dissipation of the liquid momentum, not by changing the thickness, by changing the mid-surface or the midline curvature. Okay, so imagine that you have an infinitely long film going into the board, and if you change you put some curvature into the mid-surface, you allow also the thickness to vary if needed, and this is totally consistent dynamics, and it is, they call it the visida. It turns out to be quite analogous to the elastica. Okay, in Taylor's, this was later on formulated by this seminal paper, the B&T paper, and this provided a basis for lots of work. I think a significant number of this work were done here. Not sure if specifically in how many specifically in this department, and how many in other places in Paris area by Neil Wright, and I think many other, numerous other people have worked on this in this area. So this is called the VCDA, but in all of these examples, what is changing is only the curvature along one direction. Okay, in this case, there is beautiful analogy between the behavior of still of elastic bodies, or what's called the elastica, Euler elastica, in what people call the VCDA. What was done later, and now I'm running to the 1990s, by Peter Howell, who was a PhD student at the time, or the end of his PhD at Oxford. And he asked the question, okay, what happens if I really allow the film to, I have a liquid film with some thickness, free surface, and now I allow it to vary also its curvature in both directions. So I can have what we call Gaussian curvature. Okay? And he derived a set of equations that connect the thickness at each point, the location of the mid-surface, which I call x, this is the vector x, and also the tangential velocity, consistent set of equations, which is basically just the Stokes equations in the absence of inertia, specialized for this kind of geometry. And these equations are very similar to the F-Van-Karman equation. And all that I'm going to tell you here is that we are taking this framework that was originally developed by Howell, and we employ it to understand what's going on in this problem. Okay, what you have here is just a thin film with some curvature. Once the pressure is reduced, somehow the film has to change its curvature in order to get into a flat state. And these equations are in principle described by this theoretical framework that was initiated by Peter Howell following this long history. Okay, any questions so far? Okay, so what is this framework of Peter Howell? So now let's try to be a little more detailed, and these are the slides that are going to be the most busy, hopefully also not too busy, but the most busy in this talk. Okay, so let me remind you what is a Stokes flow. Stokes flow is just Navier-Stokes without inertia. Okay, but for a planar free surface. In this case, you can describe it traditionally in a textbook. You can describe it from the point of view of incompressible liquid, and you have what we call a stream function, and you get this equation, bi-Laplacian equation of the stream function. But I would like to take a somewhat different perspective, which is as good and much more useful for our purpose, which is the following. If you don't have inertia and you have just a Stokes flow, you have this equation, right? I mean, you have the gradient or the divergence of sigma equals 0. Okay, this is just another way to phrase the first law of Newton. The sum of forces on each body at equilibrium is 0. When we move it in the continuum, when we describe it in the continuum, this is just saying that the gradient or the divergence of sigma of the tensor is 0 everywhere. Okay, and it turns out that in 2 dimensions, this is equivalent to saying that the stress tensor can be described through a potential, through a scalar potential. Okay, the exact relation is not so important. Okay, it involves the normal to the surface, but it's not so important to us. What you should think about is that if you remember electrostatics, you know that the basic statement in electrostatics is that the electrostatic field is curl-free, right? The curl of E equals 0, okay, which implies that it's conservative field, so it can be written as a gradient of some scalar potential. This is the equivalency in 2-dimensional Stokes flow. Okay? And once you do this for a planar surface, you get this equation. So now you can describe all your dynamics through this bi-Laplacian equation for a planar field. Now, what happens when we have when we take this surface and make it somewhat curved? So now the first thing is that I can still have this equation or this relation in the in-plane. So there is still a normal force in the absence of inertia. I still have this relation, but now I need to describe it. I describe my sigma with respect to the normal to the surface, but I still have this kind of function, this kind of stress function. That's one thing. The other thing that I need now to think also of what happens to the mass conservation, how the thickness is changing, and what will be the normal force balance. Okay, because in this case I don't need to worry about normal force balance. It's automatically satisfied. In this case, I need to think of normal force balance at each point also. But that's less important. Hold just 1 second. I'm going to take question here a second. The important thing that I want to emphasize is that this equation now, this equation, the in-plane force balance, is taking now this form. Namely, it's still, you still have bi-Laplacian of some psi, of some stress function, where now it's defined through the normal, etc. But now there is some inhomogeneous term, and this inhomogeneous term, which I'm going to call charge, is described in this horrible way. Now, I want to ask a quick question to poll the audience. Who knows what is Gaussian curvature and mean curvature of a surface? Good. So more or less 1/3 of the people know, and if you know, it's great. So you can follow from here what is this. If you don't know what the Gaussian and mean curvature are, I'm not going to tell you, because it's not important for this talk. Okay? All that's important here is that whenever you see this rho geo, think of curvature. Everybody know what is a surface curvature. Gaussian and mean curvature are just quantitative measures to this. But you all know that this, of course I forgot to, I'm going to ruin, or not to ruin, try to keep it without. You all know that this is flat, this is surface, it's flat, it has no curvature. This one has curvature to it, it's curved, right? This is curved. The surface of my skull is curved. You know what this curvature is, right? Even if you don't know quantitatively what does it mean. And what you have here in rho geo is the rate of change of this mid surface. As long as the curvature is not changing, you don't have anything to feed the stress, and you don't have a stress generator. If you do have rate of change of the curvature, then there is something to feed the stress. Okay? And all that I want to do in this talk, so you can read in more detail about these equations in some preprints, that hopefully a newer version of it is going to come online. But for the rest of this talk, I'd like you to think about this equation. Okay? This is the essence of this dynamics that I declared a couple of slides before. This is just Stokes dynamics of a curved fluid field. Yes, Benoit, there was a question. Yeah. Yes.
Use different ways to present. So you use the fact that the stress divergence of stress is 0, so it's equilibrium.
Yes.
Then you have an extra equation that comes from
this equation. Oh, so this equation. Yes, right. You just put this into this, and that's what you correct. Yes. Yeah. For the curved case, you have to do a little bit of work. You have to invoke the stress-strain rate relation. Okay, so I will. But this is totally analogous to what you would do if you are from elasticity to derive the Poppel-Van equation. Okay, that in the elasticity, stress is related to the strain, gradient of the displacement, and here it's gradient of velocity. Other questions? Okay. Sure? Don't be afraid. I'm not going to bite. So. Okay. Okay. Let's push a little bit further now the idea of the connection to electrostatic. So now I'm going to take a step back and remind you things that you all know. Electrostatics, but just remember that I'm doing electrostatics in 2D. Okay. I have a charge. I have a potential. Right. I call it V. It's a scalar function. I have a field. The field is the gradient or minus gradient, if you wish, of the potential. Depends how you define it. And if there are no charges, we get all the famous Laplace equation, the Laplacian of V equals 0. You just substitute this here, and you get the gradient of E equal to the Q. So in this case, it's just a Laplacian equation. And if you have charges, then you get the famous Poisson equation, right? Everybody, good. Okay, so now let me just emphasize what happens with two-dimensional Stokes hydrodynamics. Now the charge is this little beast, okay, but again, don't think of what is on the right-hand side. This is just rate of change of surface curvature. In contrast to electrostatics, you don't control. I don't tell the system how much charge is here and there. The system has to determine itself. It comes from solutions of the equation. In some sense, if you can call it as a non-linear Poisson equation. In a way, it has to be determined by actual solution of the equation, but it just has the same role as in electrostatics. Okay? And instead of potential, now you have, I could just call it psi, but it's still scalar function. in order to get now the object of interest is not a vector field, it's a stress, okay? And in order to get it from potential, you have to do a little more work than just to take the gradient of something. You have to take twice gradients and do some curls, blah, blah. But it's just mathematical technicality, okay? It's of no physical consequence, if you wish. You just think about it, psi, a scalar function gives you a stress, not a vector, okay? That's the whole thing. If I have a flat planar film, this is like equivalent to the Laplace problem, okay? Like no charges. And if the film is curved, then you get the equivalent of the Poisson equation, again with something on the right-hand side that you don't just put whatever you want, but it has to come in some consistent way by solving, attaching it also to the normal force balance, mass conservation, etc. Okay? Yes? The boundary condition, okay, that's a very good question. Boundary condition could be important, but the crucial thing here is what drives the flow is this charge. Okay, it's the rate of change of the curvature, of the surface curvature. If you have a liquid film whose curvature changes in time, that's what drives the flow. Okay? That's the quick answer. You can we can discuss also boundary conditions, and you can derive also flows through the boundaries. Okay, so even if you have a Laplace equation, even if this was zero, so it looks like there is no source of flow, you can still drive it through the boundaries, and many people have studied this kind of questions. But that's of less interest for us. Okay? Yes.
Curvature changes in time drives the flow, but the flow is also driven if the curvature is not uniform in space.
That's true. If the initial conditions are not uniform in space, they will also be forced to move in time. And this is what eventually, if you start with initial conditions in which the state is not in equilibrium, then this will start to change in time, and this will come from actual solution of the equation, and this is what's going to drive the flow. I think it will become clearer when I'm going to show a specific solution of this equation. How initial conditions in which the curvature is not fixed in time drive. Okay? Other questions? Very good. Okay. So now let's push it even further and let's discuss specific examples. Okay, so here is the most, I don't know, you go to the first class in electrostatics, well, this is in 2D, not in 3D, but you put a point charge, okay, and you ask, okay, the question you are being asked, please calculate the electrostatic field. In 2 dimension, you know that it's going to go like 1 over r. In 3 dimension, it's going to go like 1 over r square. In 2 dimension, the field going like 1 over r. Okay, you know, to solve this problem, Gauss law, right? I mean, you put a surface, etc., or Coulomb's law, you have various ways to do it. What happens now, the next order problem is what happens, so here is question number 2, this is in lecture 2 in electrostatics. You have a point charge here, and now you surround it with another charge, another ring of charge that cancel, the charge on there is opposing the charge at the center. So what will be the solution to this case? Anybody remember before I show? Okay, so you will have the same field inside the ring of charge, but outside you will have zero charge, right? Because Gauss law tells you there is no net charge. If you take any Gauss surface or Gauss line in this case, you will have no charge, so the charge is going to be zero. So the interior charge is totally screened by the charge at the ring. Let's do the same thing now for the Stokeskian hydrodynamics. So let's first imagine that I have a point charge. Okay. Now, how do I generate this point charge? You know, I cannot decide in advance what is going to be my charge, but let's imagine that it's like this. Okay. In elasticity, actually, you can do it. You can control. You can just. It's called disclination. I'm not going to discuss it, but you can imagine that you have something like this. And in this case, now we don't have a field, vector field, we have a stress tensor, and it has 2 components because of axial symmetry. One of them is radial, how much tension or compression I have in the radial direction, the radial axis, and the other one is the azimuthal axis. This is sigma theta theta. I'm not going to draw it with arrows because it will be too confusing. So I'm just going to use that the characteristic solution is like that the 2 components have the same sign at some radius. Then after this, they are going to change sign. One of them is negative, one of them is going to be positive, and then they are going to be both positive. Okay, they are going to change to the other sign. This is called disclination in the context of elasticity. Okay, Now let's try to do the analog of this case. Suppose that I have now a ring of charge that surrounds, that oppose the distributed distance, and it just cancels opposing negative of the charge at the center. And in this case, again, all that you are going to get is that there is going to be zero stress. Just like here you have zero field, here you have zero stress outside the exterior ring. Okay? Why am I going to tell you this? So you can ask yourself, okay, if I don't know how to generate this kind of charge, then how am I going to generate this kind of weird charge? And what am I going to tell you? That this is exactly the beautiful experiment that was done by Debregeas and company. So essentially what you see here in this case, in this example, is just realization of this kind of charge distribution for this kind of Stokesan hydrodynamics. Okay? And the reason for this comes from very basic thermodynamic considerations that I'm going to consider next. Okay? I see some puzzled faces, so I hope that somebody will dare to ask. Yes, thank you. Okay. Very good. This is the answer why there is a compression. Okay? This includes also the answer why, because of this nature of this charge distribution, that is, as I will argue, it must be there because of thermodynamic reasons, this is why we have a compression. So the wrinkling that you see is actually byproduct of quite non-trivial axisymmetric solution that is hidden behind all this story. It's the most beautiful, aesthetically arresting aspect of the experiment, but it actually, I would say, almost a side effect of something much deeper that goes inside. Okay? Okay, so let's move now to the next part, and now let me tell you why this is the weird stress distribution, and why this is the tape of the stress, how it looks like. So let me now remind you some basic about stress and stress-strain relation. So let's start with elastic sheets or shells. So imagine that you have elastic shell, like a spherical shell. You inflate it a little bit. When you inflate it, the material elements are being displaced from their original configuration. And gradients of this stress, of this displacement, are what we call strain. And we say that the stress, or when we integrate it over the thickness, is proportional to the Young modulus of the material, the thickness of the shell, and this strain, or the gradient of the displacement. This is in elasticity. When we have a liquid film, okay, we don't care so much about the displacement, but about the velocity. And the gradient of the velocity is what we call strain rate. And stress is being generated by strain rate. Okay? With a proportionality constant that we call viscosity, dynamic viscosity, eta. And if we integrate it over the thickness, we get another h here. Okay? So that's stress in viscous films, and this analogy is called by some people Stokes-Riley analogy. Okay, beautiful analogy between elasticity and Newtonian hydrodynamics and Hookean elasticity. Actually, this is not a complete picture because of two reasons. The first thing is, as I showed in the beginning, right? I tried to convince you why the variation of thickness is important, even if there is no tangential flow along the film, but the thickness is changing. This is enough to generate some viscous flows that generate stress. Okay? So that's why we have to add to this strain rate also the rate of change of the thickness. Okay, that's one thing. The other thing, which is even more profound, is the fact that we must have surface tension stress field. And this is different from elasticity in the following sense. So this is elastic sheet, right? I mean, and what is the stress on it? I can pull on it, and this will add to my stress. But this is totally perfect equilibrium state of the sheet, okay? Without any tension on it. If you try to imagine these things with a liquid film, it's impossible. Again, think of a soap film and try to imagine that you detach it from the ring, so it's not being held by the ring, it will evaporate. So surface tension must be there for thermodynamic reasons, for thermodynamic equilibrium. The thermodynamic equilibrium of a liquid film consists of tension. It's stressed. Okay? Molecules must pull on each other in equilibrium and being supported by some boundary forces in order to maintain an equilibrium state of a liquid film. Okay, so this means that this is how my stress-strain relation looks like. Okay, so I should say that in this part, before I insisted on the tensorial nature of the stress, because it was important for to draw the analogy to electrostatics. Here I'm just going to omit all the tensorial symbols, just to give you the idea where the mechanics of this comes from. Okay, so we have 2 gamma. This is the thermodynamic part, and this is the non-equilibrium part, the viscous part. Okay, strain rate, which includes also the rate of change of the thickness. Okay, now let's do quickly the equilibrium case. What is the equilibrium case? Well, we are close to I'm not sure, Laplace used to work, not here, right? I mean, he was in the, it was in the call, right? In the, anyhow, so somewhere here, so this was Laplace law, okay? It's always a special feeling to talk about mechanics in this area. I don't know, like all these names. So for you, it's probably like, you don't, you forget about it, but for visitors, it's always anyhow, special emotion. Okay, so Laplace law, so what happens in equilibrium? So let's do a normal force balance on this film. You can think of it either floating or freestanding. I just look at a tiny element and I try to do normal force balance here. So there is a pressure difference, so the pressure pushes this outside, so it has to be opposed by some other forces. And what is this forces? This is just 2 sigma, whatever is the sigma, the stress within the film. Okay, this is the in-plane stress, sigma is the in-plane stress within the film, and as I told you, this is just 2 gamma because there are 2 surfaces, plus non-equilibrium part which come from the viscous flow. Now in equilibrium this is 0 because there is no flow, nothing changes, no change in time, so all that we get is just the famous Laplace law, that the radius of curvature is related to the pressure difference between the 2 sides of the film. Okay. Now let's imagine that I suddenly drop the pressure inside the film. I prepare the film at equilibrium, but suddenly I drop the pressure inside to 0, the pressure difference. Okay, so now normal force balance still applies. I still need this, any piece of this film has to be in normal force balance, but now there is no external pressure difference to support it. So this relation better be 0. Now the radius of curvature cannot change fastly. Right, you drop the pressure instantaneously, but the radius of curvature is still what it is. So the only thing that can change quickly is this stress. And the way it changes is by generating viscous flows that exactly opposes the effect of the surface tension. So that the net force, the net stress that any fluid element here feels is 0. Right? Otherwise, it will be under no force balance. Of course, if there was inertia, it will start to accelerate, but I assume that there is no inertia here. Okay, it's too viscous for inertia to matter for anything. Okay, so now let's solve this problem. This is now the solution of what I showed you before. In the spherically symmetric case, the velocity, the tangential velocity is 0 because of spherical symmetry. So the only thing that changes is the thickness. The film can thicken or thin in principle. And this is what opposes, this term is what opposes the surface tension. And this actually tells you now the rate of change by which the film has to collapse. Okay? The rate, this will tell you the rate of change of the thickness, and the conservation of the volume within the film will tell you a relation between the radius and the thickness, r squared times h equals constant, and you will get the rate of collapse of the film. So this is the whole 2-line solution of this problem, or 1 line. Okay? So this is the solution, and you see why it's stable now, okay? Maybe it's not so obvious, but the stress is really 0 everywhere here. No compression. No tension, no compression. Okay, Jose, it's clear? Yeah? Oh, because I consider a spherically symmetric solution. There is no tangential velocity. Okay? Yeah. Why sorry? No, thank you for it. Okay. Okay. So yeah, no, okay, it's really important for the next part, okay? So this is a spherically symmetric solution, but now let's see what happens in our case when we have a floating bubble. And remember now what we saw in this movie. It's not only spherical, it's not only a half a sphere, but this meniscus is static. It's like acting like a clamped ring on the film. Okay? So now this solution is impossible. Then what happens? Okay? So it looks like there is no shrinking. Right? Somehow the spherically symmetric solution, or half of it, I cannot do it for a half sphere if the edge is clamped, it cannot move. So what's the solution to this? Apparently there is a solution. What will happen now is that you can now use tangential velocity, and the actual solution involves sucking of the liquid from the bath into the film. Okay? And you can do it just in a way, I can write you what is the exact solution. It's just a way that it turns out to be inward solution. It depends on the radius. It's simple solution to this problem that will tell you how you can have zero stress within the film as long as you can suck liquid from the bath. So it looks like very counterintuitive. How sucking liquid from the bath? What's going on here? Actually, it's quite simple if you think about it as a two-dimensional vacuum. Okay? So the conditions that the stress equal to zero is enforced by normal force balance and the absence of inertia after you depressurize the film. And this acts now like zero, like a vacuum, two-dimensional vacuum for the stress within the film, which is now smaller than the stress outside, which is just the capillary stress. So the liquid, the film starts sucking liquid in order to maintain this vacuum, okay, if you wish. So that's the physics here. But now, so that's what it means. The floating film remains retains its curvature by sucking liquid from the bath. So surface tension is being suppressed now by viscous stress, which is a combination of this and these two. And there is some radial flow that must be maintained in order for this to happen. So that's the quick summary of what we did. So we have this, what we call phantom bubble. Why phantom? Because it's, why? You have like a weird, very non-equilibrium shape of a bubble, right? You don't have any more surface tension. You don't have pressure inside. And it keeps retaining its shape by sucking liquid from the surrounding, from the bath. So mass and momentum conservation here are totally satisfied. Okay, mass is satisfied because the film you can determine what will be the thickness that accommodates this additional mass that comes from the inside. Momentum is being conserved because I just showed you that the stress is zero, force balance is everywhere. Okay, but something here sounds like ridiculously wrong. Okay, or at least very highly non-intuitive. First of all, of course, this is not what happens in the experiment. In the experiment, the bubble eventually collapses. In this picture, it will collapse only after infinite long time when the mass in it will be so large that it will collapse under its gravity. This is not what we see in the experiment. But even if we did not see the experiment, we could realize that something is wrong here. The state, it's very non-equilibrium state in which heat is generated continuously because of the viscous flow. But there is no source of energy for this heat. Because the only source of possible energy here is change in surface area, reduction in surface area. And the film maintains its shape. Okay? So something is wrong here. And let me now put it in a schematic way. Okay? So what I told you, this is the logical flow of the argument. Normal force balance with the absence of inertia after you depressurize the film quickly implies that the film must be stress-free. Being stress-free implies viscous flow to cancel surface tension. And viscous flow implies heat. Okay? At the same time, the same thing tells you that surface shape is static. And if surface shape, there is no reduction of surface area, and this is the contradiction. This is where the first law of thermodynamics is being violated. Okay? So a beautiful story, but where is the physics here? So here is the physics. The physics is I somewhat cheated you, not much, but somewhat. Enough to make the story coherent. I told you that normal force balance tells you that the stress must be zero in order to have normal force balance, if you have no inertia. But suppose that there is a tiny portion of the film which is flattened during the depressurization. Well, I tell you depressurization happens instantaneously, but nothing is really instantaneous in physics, okay? Suppose that it takes 10 to the minus 17 seconds or minus 20 seconds. Do I have 5 minutes? Okay, that's what I need, yeah. So it's really 10 to the minus 17 seconds. There is enough time for a tiny portion of the film, right? I mean, very tiny zone to flatten during this process. Once it's flattened, there is no more the requirement that the stress should be zero there, because normal force balance allows you to have any in-plane stress. It means normal force balance is not going to be violated if there is no curvature in this part of the film. Once you have once you have this portion, it can keep expanding. Okay? No problem for it to expand. So that's really what happens. There is a front propagation. There is a planar portion that keeps expanding on the background of the stress on a curved portion where the stress is remains stress-free. So this is the resolution, and the surface area is now being reduced because there is, right, this flat portion keeps on growing and reduces surface area, and this is what feeds the viscous flow. So where is the charge now? If I go back to the question of the charge, you remember charge is the rate of change of the Gaussian curve of the surface curvature. In this portion, there is no curvature at all, nothing to change, it's flat. In this part, it does not change its shape. Okay, so there is, it's curved, but no rate of change of Gaussian, of curvature. So the only charge is here. Okay, this is the only part in this front, in this boundary between the flat portion and the boundary where the where you see charge. So this is where we have some kind of charge. Okay, so let's go back to our picture and say, where do we have? If I look at my stress, so this is where I have the charge. This is where this is the top picture. This is the meniscus, the clamping meniscus. This is the charge, namely the rate of where the curvature, surface curvature is changing in green. I have non-zero stress inside in the flat part, and I have stress equals 0 outside. What's wrong with this? Suppose that this was electrostatic. So instead of stress, think of electrostatic field. And here there is a charge on a ring. I tell you the field is non-zero inside and 0 outside. Yes, there is a missing charge, right? I mean, this is impossible electrostatics, even in electrostatics. Okay, so you need really a charge inside to cancel this, okay? So what this charge represents, it's not rate of change of curvature, it's just a point where the description of the fluid as a two-dimensional flow breaks down, and you need to account for three-dimensional effects. But this is just a zone when the fluid is being sucked into, okay? And now what is the stress distribution? That's what we saw in the beginning. There is some radial and hoop stress. And this is really the where we have now, as was pointed out before, hoop compression, namely compression in the azimuthal direction that is being resolved, giving rise to instability, the wrinkling that we see. This is only the instability of the axisymmetric states, that the wrinkles keep expanding afterwards. And this is the analogy to electrostatic. This is actual solution of the equation of motion, including the normal force balance and the mass conservation. You see this is the hoop component, the azimuthal component of the stress. It's positive here, it becomes negative. This is the compressed zone. This is the equivalent of what I would call vacuum in electrostatics, is non-zero when the stress can be non-zero, and in the hydrodynamic case, it means that it must be flat. And this is the conducting zone when it's curved and the stress must be zero there, okay? Just like in electrostatic conductor where the field must be zero. So this completes the analogy. I will skip this part. I will just tell you that in order to complete, all the thing that we need for us to do is to tell you what is the rate of change, how this is moving, and the rate, and what is the actual charge inside. And this is all determined by consistency with this law of thermodynamics and hydrodynamics, namely the rate of change of the heat must, the production of the heat must be generated by the rate of change of the surface curvature, which is determined by this dynamic. So these are quite non-trivial equations, but they are just ODEs. Okay, only two parameters are needed to determine these dynamics. Okay, I think I'm going to scope this movie, and I'm going to just tell you that indeed you can generate a wrinkling instability from this. This is what happens here. I think I'm going to, maybe if people are interested, I'll show the movie afterwards. But I'll just tell you that I answer this question, why there is a hoop compression. It's quite non-trivial answer because of the analogy to electrostatics and because of the non-trivial nature of this new type of equation. Okay, there is a new type of equation here, new. It's not new, it's classic hydrodynamics, but you know, you get it from Stokes, but it's basically that the bi-Laplacian of the stress potential is determined not by Gaussian curvature or by surface curvature, by its rate of change. Okay, that's the new physics here, which this example is just one example. Okay, and I did not answer this question, but it's not, I hint that it's not linear stability analysis, but this may be something in the future. Before I conclude, I just want to mention this work is a collaboration with a great physicist, my collaborator, junior collaborator, Abraham Klein, junior only because he's assistant professor, not because of anything else, who is working in Ariel University, and I'm now going, which is located here in Israel's map. This is the occupied Palestinian territories. I just want to read a disclaimer. which reflects only my opinion, personal opinion, that this university, Ariel, is located in Israeli settlement in the occupied Palestinian territory, illegally according to international law. And personally, I also object to boycotting any individuals in the academic community based on their views or affiliations. And I think I'm just going to show the summary and let you ask. Thank you for your attention. And if you have any questions.
Thank you, Benny, for this nice talk, very pedagogical. We have time for a few questions. Etienne?
So do you know how well your model relates to the experiments? And in the experiments, you can control the rate of leaking, for instance, so you can probably have cases without or with wrinkles. Do you observe them?
Yes. So first of all, I should say that the experiment was done by Jesse Baird. I don't, for bad or for good, I'm not doing any experiments. There are certain aspects that are being verified by the experiments, but there are certain aspects that we can certainly not say much about. One of them is the wrinkle number, which is one of the most clear observation. I said it requires much more than what. The other thing is that we, in our theory, for simplicity, we assume a film of constant thickness. In actuality, in this case of the experiment, the film is, the initial state of the film thickness is very non-uniform. And this is because of drainage to start with. So there are various aspects that we cannot explain, but at least the initiation of the wrinkle pattern seems to fit what we are saying. Yeah, about the rate of change, it's an interesting question by itself, and this is definitely something we propose to do, but yeah.
Okay, another question.
Thanks for the talk. Very, very intriguing. One question, I understand how you construct the analogy and these solutions to understand this non-homogeneity. But do you have a general picture of how this singularity appears in the center?
Yes. It's during the depressurization period. So I told you that depressurization happens instantaneously. This cannot happen. Okay? Tell me a time, whatever time scale that you want, which is going to be very, very short compared to the viscous time scale in this problem, and I will tell you how this one is being generated. Okay, it's being generated, this kind of charge at the center surrounded by a charge, opposing charge at the front that separate the flat and the curved portion. This is all generated during the depressurization time, which could be very, very short.
So experimentally, one pushes a button maybe or clicks somewhere.
Yeah.
And so let's say there is an event.
Yes.
I do not see the equations from the experiment.
Yes.
But one sees that, at least in the picture that you present, there is a very strong non-regularity introduced.
That's correct.
There are corners.
We call it topological instability.
Yes.
In the sense that there is charge distribution that is.
So there is a connection between the push button and an appearing singularity or loss of topological regularity. Because I see strong equations,
yes.
I do not imagine the process from a theoretical perspective.
Yeah.
How these singularities appear?
It's a solution of the Stokes equations. That's with this geometrical nonlinearity. I agree that from what I said, it's not enough to, to see how it happens.
One solution, one regime, and one solution in another.
That's correct.
Regime. The bridge between these two regimes is inserting a topological change.
That's correct.
Which is a strong thing to add because it's a global.
It's not global. It happens locally, right? I mean, the topological instability happens only here. It's right. It's this tiny portion. It's here. Only here something happens. Okay,
yes.
And this zone it scales like the square root of the depressurization time. Everything happens locally. It's only here, but it's enough here to separate like positive and negative charge on the surrounding ring. Okay.
Thank you.
Okay, so unless you have a very burning question, I think we will stop there. And thank you again for the talk.